The last probability concept that we need to discuss is the idea of contingency tables. This is not so much a probability rule as it is a way of displaying information. Typically, a contingency table displays the frequency of two different variables. So we have two variables, each at a number of different levels, and the contingency table provides you with what amounts to the cross tabulation of the frequency of occurrence of each of those combinations of levels for the two variables. A couple of different concepts with respect to contingency tables. First, the marginal distribution is the distribution of one variable or the other. So if we simply look at the frequency of occurrence of variable A, typically found either along the row total or the column total, or we can look at how frequently the values of variable B occur kind of separate from variable A. A conditional distribution says let's focus in on a single row or column. So given that we are at a particular level of variable A, how likely is it that variable B occurs? And we say that two variables are independent if the conditional distribution of one variable is the same across the categories of the other variable. So in other words, if you look at a table and you look down the rows or across the columns, the distribution across each of those columns or across each of those rows is the same. Just another way of defining independence in the context of a contingency table. The best way to understand contingency tables is just to work through an example. And I like this example because it's a very practical application of where probability is used in real life. Suppose that you are responsible for an organization that does drug testing for employment. So you have to do your drug testing, your screening before you can actually be offered a job. And the tests that are used are not perfect. They're very good, but they occasionally make mistakes. So it is possible, for example, that if you've taken a drug, in this example, if you've used marijuana, it is possible that you could go in and the test does not detect that. Or it's also possible if you've not used the drug that you could go in and take the test and be accused of having taken the drug. And so organizations that do this type of testing have to spend some time and some effort to ensure that they properly calibrate the test so that they maximize the number of true positives, they minimize the number of false positives, but they're also careful to make sure that they don't throw too many false negative results either. So balancing all of that, organizations will go through, they'll conduct the drug testing, they'll look at the results of the test, and then they'll go back and they'll verify the results of that test with an independent organization. And that way they can determine whether or not the test results that they're providing are accurate or whether the test that they were using was making a mistake. So in this case, if we were thinking about the marginal distribution, we could think the marginal distribution of whether or not you get a positive or negative result. That marginal distribution would just be found here in the total in the column. Or if we want to know the distribution of individuals who were coming into this company who used marijuana versus those who didn't, that marginal distribution could be found down here along the totals at the bottom. That's what we call the row totals or the column totals. Those are the marginal distributions. Now, if I was interested just in understanding how did this test perform for individuals who have been using the drug, I could create a conditional probability and I could say, let's just focus in on those individuals who used marijuana. How likely is it that if I come in, I've used the drug, how likely is it that I'm going to get a positive test result versus a negative test result? That would be my conditional distribution. Or I might be interested in, for those who are receiving a negative test result, right? How many of those are just sort of slipping through? They received a negative test result, but they actually were using the drug. So if I focus in on a specific row or a specific column, that's what we call a conditional distribution. So let's answer a few questions based on this table. First of all, what's the probability that a person used marijuana? So out of the entire table, out of the 300 people that were surveyed or that were tested, what's the probability that a person used marijuana? So here we're looking at that marginal total. What's the probability that they used marijuana? Well, there were 122 individuals who used marijuana out of 300. So the probability that they used the drug would just be the 122 divided by 300. And if we do that math, that comes out to be about 41%. Another question, what's the probability that a person received a positive test result? So if you go into this company and you walk back out, how likely is it that you received a positive test result? So again, we're saying out of this entire 300 that we're interested in, the likelihood of receiving a positive test result, that's from the marginal distribution for test results. So a positive test result, there were 143 of those, so the probability of getting a positive result would be 143 out of 300. This is another marginal probability, and that probability is 47%. Now let's change things up a little bit. Suppose that we randomly selected an individual who was tested in this particular organization. What's the probability that that person used marijuana and they received a positive test result? So again, we're asking out of the entire sample, right? If we randomly selected an individual out of the entire sample, so our denominator here is going to be 300, what's the likelihood that that individual both used the drug and they received a positive test result? Okay, well, we can compute this directly, right? We have some probability rules, the law of multiplication, that would point us in the right direction to answer this question, but when presented with a contingency table, the easiest way to solve these problems is just to use the table directly. So here we're asking about the number of individuals who both used the drug and got a positive test result, and that is this particular cell right here. So we know out of the 300, right, that's our denominator, out of the 300, there were 119 who actually both used the drug and received a positive test result. And if we do that math, that comes out to be 0.397. Finally, let's ask maybe a slightly more interesting question. This might be a question that you would have if you were being asked to take a drug test in preparation for being admitted to a university or before you had to run in a marathon and you needed to prove that you did not use the drug. You know that you've not been using the drug, so in this case you did not use marijuana, you have not been smoking marijuana, and you want to know how likely is it that you go in and receive a positive test result anyway. Right? That would be a very bad thing from your perspective. And so in this case, we're talking about a conditional probability. We are only interested in those individuals who did not use marijuana. So we're conditioning on this particular column. Okay? So our denominator now is not everybody who was involved in the study. Our denominator now becomes the 170 people who did not use marijuana. So if we were to compute this probability, we're asking the probability of getting a positive test result given that you did not use the drug. So our denominator, when we're doing conditional probabilities, our denominator changes. It becomes the total for the column or row that we're conditioning on. In this case, we're conditioning on the column where we did not use marijuana, and the number of individuals in that column were 178. Our numerator are the number of people who have the characteristic we're interested in. So the numerator is the number of people who did not use marijuana but also got a positive test result. So our numerator here is this 24 individuals who were in that column for did not use marijuana but they got a positive test result anyway. So 24 of those. If we do that math, there's actually about 13% chance that you could go into this organization, have your drug test completed, and even if you had not used marijuana at all, there's a 13% chance that you could get a positive test result. This would be important information to have, for example, if you needed to go into litigation. If you were accused of using a drug when you know that you did not use the drug, this would call into question the validity of the test results because that 13% chance of getting a false positive result is relatively high. Again, they have to balance that against giving a false negative result because false negatives allow marijuana users through the system, and they want to balance the false negatives versus the false positives. So they're constantly having to tweak the test to ensure that they have the right balance between false positive and false negative results. So this is the idea behind contingency tables. The information is presented in a nice tabular format. You can ask questions about the marginal totals. You can ask questions that provide joint probabilities for particular cells within the table, and you can ask questions that focus in on a particular row or column that allow you to compute conditional probabilities. That wraps up our discussion on contingency tables and probability rules.